All right, everybody, this video is going to cover the design matrix and its use in fNIRS, and not mentioned it's actually going to cover very in-depth regression and the general linear model and its use in fNIRS. Due to the content, it is definitely a bit long, so bear with me on it. I'll try to get through it as quickly and smoothly as possible. All right, there we go. So a common tool in fNIRS is a general linear model, and it in combination with regression. What I've noticed is anybody entering the field, especially if you've never done much quantitative stuff, this is typically a very large learning curve, and there's not much entry-level information about it, or the entry-level stuff is either too entry-level and then the next step up is far too advanced. So this presentation is really meant to provide a fairly in-depth conceptual description and actually show how it's actually implemented to allow anybody who's using it some confidence as to actually what's going on. There might be some errors along the way, so please bear with them if they're small. I don't believe there's any large errors in this. So the concept should be fully explained and very useful. But if there are any issues, feel free to leave a comment, or if they're small enough, just kind of let them slip away, if you will. So I'll start with parameters and statistics. Personally, my own frustration with the term parameter and its use in statistics is the fact that it's used so widely. Parameters are used for absolutely anything that describes a data set in statistics. And usually, parameters are meant to explain the mean of a data set, or the standard deviation of the data set, or the variance of a data set. But as you get more complex and more aspects of data that you want to describe, they can also be things like characteristics, such as height or weight or volume. So it covers a very wide range. And what I find frustrating about it is when you don't know much about statistics in particular, when you come across something that is so broad, it's hard to understand it because too many examples exist. There's not one specific category you can really clump it in until you understand a little bit more about it. One additional parameter that's not mentioned is slope. So slope can explain a data set, but that's kind of confusing because each parameter you add to something like a regression formula, regression equation, will actually have something called a beta unit attached. That beta unit actually has a slope, or is a slope. So if you use slope as a parameter, that parameter would have its own slope. So it's kind of a slope having a slope, which is kind of confusing. So for the case today, we're going to kind of ignore slope as a parameter, and we're just going to use it as this beta value, which we'll talk about later. To summarize a parameter as best I can, I would say that it's a basic component that can be used to explain another component. And you can use any component to explain any other component as long as there actually is that relationship. One of these parameters, as I mentioned, would be mean. Mean is kind of the most basic and probably very powerful tool to explain data sets, but it has severe limitations. And this example on the right should show that. So I have two data sets, one's in blue and one's in kind of an orange color. One has a positive slope, one has a negative slope. So one's rising over the x-axis, one's decreasing over the x-axis. But they both have the same mean value. That's problematic. So if you were to actually compare these two data sets just using mean, they'd be identical. And clearly, visually, you can tell they're not. So if you were to write a formula for that, it would be y equals mean of x. So you just put in the mean value here, the data sets here, and you create a mean value. So this would be your explanation, essentially, of the data, and y being the explanation, not this y-axis here. So one step beyond that would be a slope. So taking the mean, well, now we'll tilt it. What if the data's shaped in a different direction? So we'll go ahead and tilt it. And you can tell we have two slopes here for the two data sets, and they're much better fit. You can see that the lines tend to follow the path of the data. So now, using these slopes, we would actually be able to explain our data set much better, or predict it much better. So if you were to look at the x-axis, it goes from about 0 or 1 maybe to 20. If you were trying to guess where number 21 would be, just follow the line up, put the point at the appropriate cross-section, and you would get your output. So that would lend to this formula y equals mx plus b. In this case, y would actually be this guy here. So we're actually looking at a line with some component to it. The m is going to be the slope. So this is going a little bit more deeply into, we're creating a line formula, which I believe is probably middle school or high school algebra. If you've taken a lot of math classes, it's something that you will never, ever, ever forget. So now we have y equals mx plus b. Y is the output. Y is the output that you're trying to solve for or predict or whatever it might be. M is the slope. So we'll get to that in a bit. X is going to be what you're actually putting into the variable, and then B is what's called a direct current if you're into electronics, a baseline if you're into any kind of measurements, any kind of time measurements. Or you can also think of it as whenever you don't put anything into the equation, your starting point, where would it start at? So kind of, you can, let's see, if you're renting a car, you usually have to put $50 down, then you pay per mile or something like that. That $50 that you put down, no matter how many miles you drive, you at least pay 50. That would be this B aspect. So one intro note, we're not going to dive into it too deep yet, but I want to mention converting this y equals mx plus b to something in fNIRS. The y could be thought of as the resultant signal at that channel. The m would be the impact that a condition would have on that output. The x would actually be a GLM. The GLM is kind of like your conditions time series, and we'll get into that later. And then B would be kind of like your rest or your inherent variation in the signal. So again, don't focus on that too much, but I want to mention right as we're looking at both formulas, you can see the comparison, and then we'll explain it in much more detail as we go. So the one thing I want to mention, though, is we have a line formula, which is great, but maybe it doesn't explain our data fully. So we can actually go a bit further. And instead of saying y equals mx plus b, we can use statistical notation, which actually bothers me significantly, that we've converted from a very easily memorable formula to something a little bit more complex. That is y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, and it goes on and on and on. The most simplistic version of that would be y equals beta 0 or beta naught plus b1 x1. And so you'd stop at this point right here. And that would equate to y equals mx plus b. The b term has flipped. Beta naught is now your b. The little x has been swapped for a big X, notating that it's a matrix. And the little y has been swapped for a big Y, which again will be a matrix. I'm very frustrated why they didn't just keep it as y equals m1 plus m1 x1 plus m2 x2, etc., and then put b at the end. I think that makes sense to me, but I'm sure there's some reason for it, but it's always been something that has irked me. So it starts to look a little scary at this point, but it's really a basic idea, and we're going to dig into that. So this is all of a sudden jumping from line formula into regression, which actually is the same thing. A line formula, y equals mx plus b, is technically regression. It's just no need for a fancy term because it's a very simplistic formula. So really it's just what you're taking is many lines in many different dimensions and trying to figure out how they relate to one another for a common output. So let's say we have a very basic example. We have two parameters. We're not going to use mean, variation, or slope. We're going to start using something that's a little bit more, let's say, relatable. So we're going to use age and education to impact income. And keep in mind, this is totally made up data, so don't rely on any of the details or the output. But we have a little sample of 20 people that I made up. And we have their ages, we have their education level, how many years they've spent in school, and then we have how much money they make per year. So the first graph is on the left, and you have age on the x-axis, you have income on the y-axis, and it's in tens of thousands. So the first 0.2 is actually 20,000, and it goes up from there. And you see as people get older, they start to make a little bit more money. That's good. What you also see is as they get older, the variation spreads quite a bit. That's actually not very good. We're going to ignore that for now, but just note that that's something you actually don't want. How the variation changes over that. The view on the right is going to be education in years. So it goes from 10 years of education all the way up to 19 years of education. So essentially you have like almost through high school, all the way through college and then beyond. So, and you see the variation is widespread on that, but also tends to go up over the years. What I want you to note is there's a slope of the line, and there's also this norm of residual. That's something MATLAB uses to just give you kind of goodness of fit. It just says how tightly squeezed in the data is, and I believe it's actually the smaller the amount, the better. So the graph on the left fits the data a little bit more than the graph on the right. And there's another thing called R squared, which is more widely used, but MATLAB readily gives you this. Okay, so as a researcher, you have the option to explain income with one of the variables, and we're going to use the statistical notation for the line, and that would be y equals beta naught plus b1 times the age. And the other option would be to explain it using education, y equals beta naught plus b2 times education. And this can be either one of these. You know, they're two separate formulas. We're not including them as one yet. They can be thought as a one-dimensional line, and it's on a 2D plot. So if we go back one, you have your one-dimensional line on a 2D plot, x and y, okay? Fairly simple. But you can actually combine the two variables, and you can combine them potentially because maybe your outcome, the income, is not solely explained by age or solely explained by education, but it's explained by a combination of the two. So you actually want to see not necessarily the interaction between the two, but you're wanting to see, can I more correctly predict someone's income if I include their age and education rather than just their age? So that's a very useful thing, right? Somebody could be 60 years old and have 2 years of education versus someone who's 30 years old and has 15 years of education. It's more likely that the 30-year-old's probably going to be making more money than the 60-year-old simply because of education, not because of age. However, you get two people with the same education and a person who's older will probably make more money. So they actually do make sense, right? To actually look at these together. So on the previous slide, the normal residuals was smaller for education. So going back, you see the normal residuals that MATLAB uses. And again, we're looking for a smaller number, so 1.5 versus 2. Okay, it's smaller. So we could argue that age is a better model for income than education. But how do they look together? So we're going to make what's called a design matrix. Design matrix is actually very simple in this case. It can get more complex, and we'll make it more complex down the way. But it's very simple in this case. All we're going to do is take the data. We're going to take the age, and we take the education. We're going to smash it together, and each version will have its own unique column. So we start with an array. So here's age, and here's the numbers that I used. We rotate it, so we flip it vertical. We take the education array, same thing, number of years, and I flip it vertical, and we like that. Then we're going to put them together. If you're doing it in MATLAB, it would look like this. So make your age variable, make your education variable. Probably don't use the curly brackets. I use those because they look nice. You actually would just want to use square brackets. And then I would create a big X, and I would take age. This means that you flip it sideways. Take education, flip it sideways. And then each column would now associate with a beta value. So this is what it would look like. We have income. Here's my array for income. We have beta naught. We're going to ignore that for now, but you probably shouldn't. We have beta 1, which is an unknown. And we have age, which is my ages. We have beta 2. Again, it's an unknown. And there we go. Here's the actual design matrix here. These two columns here, if you notice, it's age and education, age and education. What I did over here was actually just grayscale it, because a lot of times you'll see these actually done in black and white, and you can clearly see two columns. And the first one is just slowly increasing over time. The other one kind of oscillates. And you can see the oscillations much more clearly because the little dark rows are the oscillations. So here's a nice divot and here's a nice divot. But then it kind of peaks and valleys and all that. So if you can think of it, these are kind of individual components, and they're individual parameters in this case. Okay, so again, creating the design matrix, you're going to have it as this, and then you want to actually perform regression. And what's kind of cool is really what you're trying to do is figure out what these beta values are. And to do that, MATLAB has this nice built-in function called regress. And I basically put in income. I flip it so that it's in the appropriate direction. I save it as betas because I'm solving for my betas. And then this is the outcome variable. This is the income variable. So what it spits out is two values, and they're just scalar values. The first value is for the first column, the second value is for the second column. So keep in mind the first column was age, the second column was education. And also keep in mind that beta value is essentially slope. In our case, and especially this case, it is slope. That is what we're looking at. As we get into fNIRS, it's going to get slightly more complicated than that, but in essence, it is just slope. What I get as output is the beta for age was 5,065 and change, and the beta for education was actually negative. And I may have made an error here. I haven't found my error. I've dug into it a little bit. But what my data said was that as you have more years of education, you lose money. So my values that I made up were probably not correct, but we're going to pretend as though they were. So what this says is that for every unit increase in age, you can expect to make $5,000 more, $5,065.38 more per year. For every unit increase in education, the expected income actually decreases by $6,520.06. I would be disappointed if that were the case, but I don't. But keep in mind it's totally made up data, so don't hang too heavily on that. So each component in the design matrix columns are multiplied by their respective beta values to give the resultant output. The reason that this slope, so if you go back and you look at the graphs, this actually had a positive slope. So it doesn't click too readily that it would have a negative slope now, but it's actually, it can make some sense. It's probably not overly likely that this will happen often, but it makes some sense because there's something called an interaction effect where you're actually looking for a specific effect between two variables. But this is not what we're looking for, but these variables are related by the person connected to it. So while individually increasing in age will lead to higher income, there's a strange effect with the person having more or less age or education that ties into the slopes changing individually. So again, it's unlikely that it would go from positive to negative, I think, which again, I may have made a mistake along the way, but it will change. It's not going to be the exact slope that you receive just from the age put into the outcome, or income in this case. So this impact alters the individual slopes or impacts the way that each parameter has on income, if that makes sense. So this is what we see. So what I did here was actually take this is age, and I multiply the age by the beta value. So you get the beta value of 5,000, and you look at age, and you go up through here. So you actually get an output of the combination of the two. First off, that's almost a perfect line. You get this fantastic diagonal. With education multiplied by the beta value for education, you actually can see now the decrease in dollar amount for age and education on income. So interesting output, but again, if there's an error here, don't worry about it too much. Just realize that as you put this in, things will kind of alter along the way because of their kind of combined relationship. So because we have y equals beta 1 times age plus beta 2 times education, we actually have a three-dimensional graph. Normally you would have y equals mx plus b. You have x, which is your input, that's your x-axis. Y is your output, that's your y-axis, and it's two-dimensional. That's it, and your regression line is just a single line. In this case, we have two inputs. So we actually need two axes for the inputs, and usually that's going to be an x-axis and then maybe like a z-axis going backwards. So what we have over here, I don't know if I can, no, I can't rotate it, is essentially a three-dimensional graph where the points are not only laid in x and y fashion, but also with a depth. And so now your regression line is kind of, you can think of it actually as a plane. It's like a 2D plane going up. And because of that, you can have variations in age and education and their impact on that. So you don't have to have, okay, you're 30 years old, every 30-year-old had 15 years education. That's going to vary as well within that. And again, we remove this beta naught here in the example. So what we have is the actual formula, the actual equation is y equals, this is the beta for age, plus or minus, there's a negative here, the beta for education times education. It's going to be a little bit tricky to visualize this, and as you add more and more and more and more parameters, it becomes almost impossible to really visualize it. But it's all there. Each one has a different direction of the slope going in whichever way, and it allows you to pinpoint, based on that regression line, if I had this parameter at this point and this parameter at this point, where would my outcome be? Okay, so that is regression. And I hope that was helpful. I think that answered some questions that I've always had along the way when digging into things on regression. So I do hope that was helpful. But now I actually want to show, okay, we did it on age and education and income. Let's actually see what it looks like in fNIRS. So now we're going to have a lot of similar concepts, but we're going to use it in a very simplistic kind of fNIRS experiment style. The first thing that you have to ask is, what variable is the regression actually trying to solve for? In the example before with age, education, and income, you had two independent variables, which were age and education, which would vary, and the dependent variable would be income. In a very simplistic fNIRS experiment, keeping in mind that these can get more complex, you can ask other questions, you can do all this, but a very, very typical and simple experiment, the independent variable would be the hemodynamic response for each channel and also each condition. The dependent variable would be the condition. So you're going to alter the condition to see if that specific channel had a different response based on the condition. Essentially, what we're getting is a two-dimensional graph with a one-dimensional line. But we are also looking at time. So keeping that in mind, time series data has some uniqueness to it. In the previous example with age and education and income, there's really no aspect of time. These people were sampled individually one time. There wasn't a continuum of it. What you could do is say, you could graph age through the years of one person and track it over time and see the income fluctuation. That would be a time series data set. But for the sake earlier, it was not. What we deal with fNIRS, it is. So a very basic idea would be y equals beta naught plus beta 1 x1, where x1 is the data from the condition 1. And you're looking for the response on the output. Beta, you're going to figure out what the impact is. What is the slope for that data, for that aspect to impact the response? In condition 2 would be the same, but you'd have beta 2 x2. And again, each condition and each channel will receive its own model. Let's see. And also keep in mind that those big X's, those big Y's are actually matrices. They're not individual values. So we've again removed beta naught just for the sake that it's rest. We're going to assume that it's 0. That may not be the case, but I think that's fairly common. Okay, so because we're dealing with time series, our areas of interest Well, first off, the time points are related to another, which gives you some uniqueness in statistical tests, which we're not going to cover in this video, but just know that there's some interrelationship between time points. But also our conditions are, our age previously was just one time point. It was an age, or our education number was a number. But in this case, our conditions are actually like spans of time. We did a condition for 10 seconds, or we did a condition for 30 seconds. So normally you will actually use a window for that. And yeah, typically the window is about 20 or 30 seconds for fNIRS data. Of course, that can be very different depending on your application. So for our sake today, we're going to assume 20 to 30 seconds. Once you have it windowed, you can model each of those windows. So let's say I have condition 1, tapping my left hand, and I did it for 30 seconds, and I stopped. Then tapped it again for 30 seconds, then I stopped. I can actually model every single one of those windows individually and get a beta value for each one of those individual aspects. That's fine, but we're dealing with brain data. And any data really is very useful to do something called a block average. And that's because it will actually average together groups of similar conditions and get you an average signal. What that does is go to eliminate any noise. It eliminates cyclical things that aren't really part of the data of interest. And it gives you a cleaner and more reliable signal. So once you have these together, you can actually overlay them, get your average, and now you have this average response for that kind of condition. And keeping in mind that it's not just a number here. You still have a window where things are changing in the window. So it's a time series for each channel in each condition. It looks something like this. I just did a little Gaussian here, but think of it as this is a response of hemoglobin coming up. The idea is that we want to actually explain this. We're trying to predict, we're trying to explain, we're trying to do something like that. And so we're trying to figure out what's the best way to do that. Well, we could try slope, but as you can see, I fit a slope to this, and it doesn't tell you much at all. In fact, I don't think that really tells me anything. So not really useless. Some groups will focus on different time aspects of this and fit a slope to it. Maybe that's their thing of interest, their parameter of interest. But if we're looking at the full signal, this is pretty not explanatory. I can even, as I note, I could picture a response identical to this, but just much, much smaller that has the same slope. And again, very different sizes of response, but you would, if you use slope to measure them, you wouldn't get anything useful from that. We could also do peak value, and I kind of giggled when I made this, but again, you have a nice response pops up, and you could say, okay, well, I'm just going to look at the largest value. Well, what if you have something like this, and for some reason you had some noise or something that just shot up? Well, use peak value here. It's probably not very reliable. Something can peak up, peak down, and it really causes some mistakes in the data. So again, you're welcome to use it, but it's probably not your best option. Again, it doesn't tell you much about the data. So you have, again, some options. You can do a one-dimensional line. That would be the slope. Probably not very useful. Let's see, with time series data, again, if you have a 2-parameter model, it would be a two-dimensional plane. With time series data, we're not dealing with a 2-dimensional model, a 2-dimensional plane, but we're going to use something that really details the timing aspects of the signal. In our case, we use something called the general linear model. General linear model is really a umbrella term, just similar to parameters. And really what it's saying is it's a fancy term for fitting a specific shape to the model rather than a straight line. In essence, actually a straight line is technically a general linear model, but usually we'd call that a regression line. So it gives you more variety as to what you want to fit. Not just a line, but you can fit a bump, you could fit a square, you could fit a triangle, you could fit different types of shape to fit different types of activity. In fNIRS, the common, what's called a basis function, is the canonical hemodynamic response function. It's also called the HRF. So this is an assumed response. You go into your data saying, if that brain area is active during this condition, it will look something like this. And this shape has several parameters. You can move that bump where it starts. You can see there's a peak value in that bump around 6 seconds. If I wanted to, I could push it to 12, 18, wherever I wanted it. I could make it fatter. I could make different aspects of its shape, change shape. But the one you see on the right is very, very, very standard. And again, that's called the canonical hemodynamic response function. There's many others, and they do impact the output, but we'll get into that. The reason that it's used is, let's say you have a 30-second window. You have a 10 hertz sampling rate. That's 300 time points. In 300 time points in brain activity, it's unlikely that brain activity just goes up. It's gonna oscillate. It's the brain. It does a lot of things at any given moment. So luckily, we've done enough hemodynamic experiments, and I say the field, not me in particular, that we have a fairly good idea of what shape due to activity looks like. And it looks something like the HRF that we showed there. The exact shape is quite arguable. So there are other options, and other groups will tout other options. But the one mentioned is widely used and acceptable for most cases. If we want to implement this shape into what we were talking about with regression, and again, we had the incomes example where we have age and education, where in those age and education brackets, we literally just put data. We had the data, we put it in. Well, now, where instead of the data, we're going to be actually using the data to solve for the beta value. And we don't really have our input variable is actually almost our output variable. We're using data to model data, which is kind of screwy. We don't have like in our case, there's age for income. We have hemodynamic response for hemodynamic response. We're going to use a model. And what that model does is give us a level of activity. So instead of putting in our actual data into this little curly bracket, we're going to put that shape. I'm going to overlay that shape in time, if that makes sense. When we solve for the beta value, and if you think about it, really all we're doing is taking the response, basically dividing by the HRF, and you solve for that. So basic math. There's a little bit more to that with some, I believe there's some convolution or something thrown in, but that's essentially what you're doing. That's really what we did here as well. But what you're doing is solving for that beta value. And the beta value, again, is the exact same thing as a slope. A steeper slope means there's a bigger impact for that variable on the output. The difference is we don't have a line, we have a shape. So the bigger the beta value, the more the shape grows, or the smaller the shape grows. Well, the bigger the shape, the bigger the impact. So it's going to be the bigger the activity, if you will. And showed that below here. It's it's not just a steepness here. It's many different kind of like scales. So the beta values again are basically how well or how poor the data fit the ideal response. Considering the ideal response, did that channel during that condition fit what I expected? And how well did it fit that? If this part here fit it really well and this part didn't fit it very well, I'm going to assume that this part was more active than this part. So what this does is kind of interesting. We use a fairly complex shape. It has several parameters. I don't know if you saw that in the last one, but you can see parameters 1, 2, 3, 4, 5, 6, 7. There's 7 parameters here. And again, parameters using a fairly broad term. But there's 7 variations, things that I can vary in this function here. And it changes the shape. We use a very somewhat complex shape. But in doing that, It allows us to explain the data in better detail than a straight line could offer, than a mean value could offer, than a variation could offer. It gives us more variety, but it also simplifies the statistical method, because what you would have had to do in many respects is compare each time point in one condition versus each time point in another condition. And you have an enormous amount of comparisons. Again, that 30-second window with 10 hertz, you're comparing 300 time points against 300 time points. And each time you do a comparison, you're more and more likely to basically mess up your statistics. And it's type 1 error typically, but you're more likely to get screwy results. But instead of doing that, what this gives us is our beta value, which is, again, the weight of how well it fit, and which now we have a single number to compare. So now you have fewer comparisons, which is lovely. And you've gotten fewer comparisons by using a complex shape, which actually explains more, which is quite handy. So again, the beta values are typically what's actually tested for. These will be run through an F test or a T test or whatever test you're running. And again, the T test, and saying two conditions, would compare beta values for a specific channel from one condition for that same channel in the other condition. And you do that for all channels. So again, you still have a lot of comparisons, but it's far fewer than you would have had. The larger that difference between conditions, the more significant the condition's impact was on the brain activity. Again, the advantages to this is, first off, mean and slope are out of the question. It's too simple to explain the data. The GLM offers more complexity, and it also it kind of acts like a mask for your data. It says, I'm only interested in this little bubble of time, whereas I'm not interested in, let's say, that 6-second peak. And I'll actually show you real quick. So right here, you have kind of, I'm interested here, is essentially what this is saying. I'm not interested over here. So anything that peaks over here, I'm going to almost ignore. So that's very handy. So it allows you to rule out information for non-experience, so other brain activity to some extent. It also allows you to rule out noise. Anything that doesn't fit that model doesn't really impact the model that much, or it impacts it less. It simplifies the time series. So it simplifies hundreds of, if not thousands of data points to a discrete value, so a beta value. And that limits, again, to an extent, the statistical comparisons needed to be performed, and therefore decreases your type 1 error. You're still going to have high type 1 error because you have a bunch of channels you're comparing, and potentially a lot of conditions, hopefully not too many. But ideally, you're having lower type 1 because of that. It also allows you for a more objective comparison between conditions. This is kind of my argument. I don't know if many people would agree with me, but really what it does is say, I have this thing and this thing, but instead of saying one of them's right and one of them's wrong, or saying both of them right or both of them wrong, whatever it might be, I'm taking the problem to a third party, which is my GLM. I'm going to say, this is going to be my gold standard, and I'm going to compare both of those to it rather than compare them directly to each other. So it kind of helps with that sense. There are a lot of disadvantages, so don't feel like it's some magical pill. So there are many models. I showed you one. If you choose a different model, or if you vary the model, it could greatly change your results. So you could go from totally significant results to nothing, or the opposite. So definitely make sure if you're using a model, you have enough evidence to have a reason for it. Don't just grab at it and guess. Additionally, your question may not be ideal for the model. One really good example is, let's say you have two widely different populations. One's either pathologic, or perhaps the age difference is vast, maybe 6-year-olds versus 90-year-olds. The brain activity in a 6-year-old is probably very different than a brain activity in a 90-year-old. And that shape may be different between the groups. So if your question says, is the activity due to this condition different between my 6-year-olds and my 90-year-olds? Well, activity is specific. So you would have to model your 90-year-olds separately. You get beta values from that model. And you have to model your 6-year-olds separately and get your beta values from those, and then you would compare. That's kind of screwy because you can favor your populations and you can really use that to your advantage and not be too honest about that really easily. So if your question is the activity different, you have to get raise a red flag on that and make sure you're doing honest work. If your question is just, are the groups different, then using a general linear model is fine because you're comparing to this third-party gold standard. So the 90-year-olds compared to this versus the 6-year-old compared to this will be different. That was your question. You're fine. Back to that same comment of how your question is shaped. This has also caused a lot of groups to search into kind of the machine learning realm. And the GLM forces you to squeeze your data into some container that you hope is right. And you should have very good reason to think it is right. But it could be wrong. And this has gotten a lot of groups more and more interested in what's called data-driven or data-centric rather than model-driven or model-centric, which is the GLM methods, and use different learning algorithms to dictate whether or not something is active or not active. And I have LDA and SVM. LDA stands for Linear Discriminant Analysis, and SVM is support vector machines. Both are very common in the field. So going through all this, this should give you a fairly good idea of how this is, how it functions in the background, and actually what's actually happening in the fNIRS realm or the neuroimaging realm. And hopefully when you get around to it, you should have some confidence in, okay, I know what I'm actually doing and the output makes sense. So anyway, I do hope this was helpful. I know it was a little bit longer than I typically like to do, but I think it was fairly important to dig into. But again, if any mistakes were noted, feel free to leave a comment so other people can notice it as well. And otherwise, I hope it was helpful. Thanks, guys.